Hello, I'll be talking about teaching engineering physics to neural networks, the case of Reynolds equation. To begin, neural networks have been used to solve physics governed by PDEs. One such method is popularly known as PIN. PINs work by modifying the loss function of the neural network such that instead of basing it on training data deviation, we base it on the residual of the PDE. This makes PINs unsupervised learning methods, eliminating the need for training data. Pins are intended to replace traditional FDM solvers. This is because FDM solvers can be time consuming, grid dependent, and not scalable for a high number of solutions, making them unfit for optimization. Pins, on the other hand, have advantages such that small inference times, they can query the solution at any arbitrary point, and they can leverage automatic differentiation when needed. The problem statement is to simulate fluid lubrication in a journal bearing while accounting for phase change because of cavitation. The geometry is shown on the right and the governing equation is shown here. This includes a forcing term H depending on the geometric theta gamma and involves two terms. Some challenges of this problem are its high nonlinearity, hard physical constraints, as well as a large input domain. Rom et al. Implemented a pin to solve this equation and demonstrated how it could work. However, this work ignores the tilt gap height contribution and restricts the domain to only three variables, which makes the problem much easier and simpler to solve. The entire problem that is being solved is shown here. It involves the PDE, boundary condition, a periodicity constraint, and a phase change cavitation constraint, the details of which could be found in the report. The neural network structure itself consists of three features. It has an input layer with the five features, two coordinates and three geometry. It consists of an embedding trunk structure and a head structure that gives us the final output. The loss formulation is the central feature of a pin. The loss is formulated based on the PDE residual, and the derivatives required for the PDE can be calculated directly using automatic differentiation. The individual terms are the residual, the boundary condition, the cavitation constraint, and the periodicity as mentioned previously. These are all calculated at individual points, and their sum must go to zero while adjusting the weights of the neural network. The sampling strategy involves collocation point generation using constrained Latin hypercube sampling. An example of which is shown on the right. This is followed by an adaptive residual sampling. This is because the input domain is very large and the sampling is sparse, and there are regions of high local nonlinearity. Therefore, every few epochs we add new collocation points with probability based on the local residual. The training is carried out similar to a normal neural network using an NVIDIA A100 GPU. It consists of two stages, a global search using Adam and a local search using BFGS. The results are shown here. Looking at the convergence plot, we see that the training loss decreases rapidly, and the huge spikes in loss are when we are adaptively resampling. Thus, to prevent overfitting, adaptive resampling is actually necessary. The results were validated using an FDM solver built from scratch, and the following geometry was input to the model. Interesting to note that this inference point falls outside the training range. The model has never seen this before, and it is an interesting case to study. Looking at the results on the right, we see some qualitative features of the physics, the pressure buildup in yellow and the cavitation boundary in blue. Uh, However, the pin still has some trouble in predicting extremely sharp gradients and the boundary condition on the left side of the domain. Quantitatively speaking, there is still some large error in prediction of about 0.345 in L2. This could possibly be addressed by further hyperparameter tuning and better sampling strategy. The evaluation time is when the pin truly shines. We see almost a 10,000 times increase in evaluation speed for the pin, and the break-even point considering both training and evaluation is about 16 simulations. This means that when we are conducting more than 16 simulations, pins will be faster. To conclude, a working proof of concept for pins was shown with an reasonably accurate result and a high speed up. Further work could involve more complex PDEs as well as a hyperparameter tuning. Thank you.